Welcome to SanfordFlipMath. This is PreCalculus. We are working through the Demana, Foley, Kennedy book. We are in Chapter 6, dabbling with parametric and polar situations. This is 6.4. We're going to work with polar coordinates, and polar coordinates are coordinates that identify locations in a graph in a way very, very different from how you are used to identifying locations on the flat surface. You are used to using what are called Cartesian, named for Descartes, or rectangular coordinates, where x and y, x is the distance to the left or right, and y is the distance up or down, and so you might be considering a point like maybe if I look at 2, 3, so you go right 2 and up 3, and that's a point. Okay, so I'll call it P just for that point. Probably should call it R for rectangular, because that's how we got there. Okay, well, polar coordinates have a whole different setup. Instead of x being left and right, y being up and down, the first number is actually r, which is a radius or distance from the pole, and the pole is what we normally think of as 0, 0, the origin. And then what you do is you rotate an angle to find that location. So for instance, if I had maybe the ordered pair, let's say 3, 120, assuming degrees, then I would count out that's 0, 1, 2, 3, so this is the pole, and then I would rotate around to 120 degrees, and I would put a point, and I'm going to call that P for polar. Okay, so this is that ordered pair 3, 120. It's just a very different way to locate things. Okay, so let's just do a couple more examples. Let's say we have the, let's call this Q. Let's say 1, negative 90 degrees. Okay, so if I go to 1, and then I rotate negative 90 degrees, remember a negative rotation is clockwise. Positive is counterclockwise, just like when we were doing all that trig stuff. So this is that point Q. Okay, one more just for variety's sake. Oh, I need a different color, sorry. Let's call it R. And no, I can't call it R because that was for rectangular. We'll call it S, I guess, whatever. Let's do negative 2, 180. Okay, so negative 2 would be going, instead of along the positive x-axis, what we think of as the positive x-axis, we go negative 2, and then 180 degrees again is still counterclockwise, so I'm going to go, okay, here's 90, and here's 180, so something like that. So this point would be point S. Okay, so a negative radius goes the negative direction, so to the left instead of to the right. And now there's nothing wrong with doing the angle first and then going either towards it for a positive R or away from it for a negative R. Okay, so this is just kind of weird, and it'll take a little practice, but there's nothing real deep about it. Okay, because we have two different systems, we actually can move between those two systems. Okay, so as you know, the Cartesian or rectangular coordinates are x, y, polar coordinates are in theta. Well, just like back when we were doing all that trig, x happens to be equal to cosine theta. So let's draw a little picture, a diagram of what's going on here. If I put a point here, this distance would be x, this distance would be y, this distance this way would be r, so this is xy, and this angle would be theta. So this is also the ordered pair r theta. Okay, and just going with stuff that you already know, there's nothing new here, it's just reminding you in a different context what's going on. Okay, so some things like for instance, um, oh, this is wrong. That's supposed to be R, and that's supposed to be R. Ooh, caught myself. That was close. You're familiar with the Pythagorean theorem. You've been doing this forever. X squared plus y squared equals R squared. And tangent of theta, well, that's opposite over adjacent, so this is no shock, y over x. Okay, so these are typically used when going rectangular to polar. If you want to know what r is, then x squared plus y squared equals r squared. If you want to know what theta is, well, start out with y over x and then do inverse tangent. Okay, so theta typically is inverse tangent of y over x, but then you have to ask the quadrant question. You know, what quadrant am I in? Okay. Well, going the other way, you know that cosine theta equals x over r. Well, if r isn't 1, then it's there. And then to get x itself, we have to multiply both sides by r. So let me correct this. X equals r cosine theta. And in the same way, y equals r sine of theta, because sine would be opposite over hypotenuse. Okay? All right, so this is for going back and forth. So let's just do a little example. Okay? So let's say I have the ordered pair, let's say xy. Okay, so this will be in rectangular. Let's make it -2, 5. So -2, 5. Okay? So what I'm going to do then is figure out what r and theta are. That's what I want to know. I'm going to make this into polar. Okay, so r and theta. Okay, so r equals, well, r squared equals -2 squared plus 5 squared. So this is 4 plus 25, or 29. That's what r squared is. So r is the square root of 29, which is 5 point, I don't know. All right, I cheated. It's 5.385. Okay, so that's r. Okay, now we need theta. Now, I didn't specify theta in degrees or radians. It can be in either. Now, if this was a calculus situation, it would have to be in radians because everything about calculus and trig is in radians. But here I'm just going to go with degrees just to make your life a little bit easier. Okay, so tangent of theta equals y over x. Well, y is 5, x is -2. So I'm going to do inverse tangent of -5/2, and I'll do that in degrees. Okay, so inverse tangent of -5/2. Okay, I'm in degrees. Okay, so inverse tangent of -5/2, and you could do 5 over -2, it wouldn't matter. Okay, so -68.198. Okay, so -68.198, I think is what it was. Let's call it 199. Okay, now I have a little bit of an issue though. If you recall, if I come out 5, yep, remember I'm trying to get to here. If I come out 5 and then rotate -68, I'm in the wrong quadrant. Well, I need to fix that. Now, there are actually two different ways to fix that. One way is to change the angle. One way is to change r. Now, sometimes you can't get away with changing r. But so what I'm going to do is these are apart 180 degrees, so I'm just going to add 180 to this so I can get in the correct quadrant. Okay, so I'm going to pop over the calculator for a second and just say plus 180. Okay, so 111,801. Okay, so I'm going to call that 111,801. Okay, so my ordered pair is, if I'm rounding, 5.385. That's the r value. 111.801 degrees. Okay, so just again, 5.38. Come out 5.38, and then go 111. That's a little more than 90. That puts me right here. That gets me to the same spot. Okay. All right. Now, just a quick little note here. I could have done instead the same r theta, well, the same point, 5.385 and negative 68.199 and made this negative. So if I would have done that, it would have been negative 5 point something and then rotate backwards. And I still would have been to that same spot. Okay, I know that drawing's getting kind of busy. Okay. Okay, well let's do one that goes the other way. Okay, so let's do an r theta equals, let's say, so we'll call this P for polar. Let's say negative 2, and let's do 2 pi over 3, I guess. Okay. All right, so this is a little bit more straightforward, a little less thinking because it's pretty automatic. Okay. So x is r cosine theta, y is r sine theta, and really you just plug and chug on this. This is pretty straightforward. Remember, this is the r, this is the theta, so negative 2 times the cosine of 2 pi over 3, which is negative 2. Cosine of 2 pi over 3 is actually the square root of 3 over 2, only negative? No. All right, let me just stop for a second and do a little unit circle. 2 pi over 3 is 120 degrees. Okay, and the ordered pair here would be square root of 3 over 2 and 1/2. That's negative. All right, cool. So times negative 1/2 equals 1. Could I have just typed that in the calculator? Yep, sure could have. So again, our sine theta, so negative 2 sine of 2 pi over 3. Well, sine of 2 pi over 3, I already have the ordered pair over there, or the, from the unit circle, so that's going to be square root of 3 over 2, and so that's going to be negative square root of 3. Well, that can't be, can it? Oh, yeah, it can. I'm mixing up my unit circle with this. Okay, don't do that. Okay, so let me tell you what I mean. It's really useful to have a picture of where this point's supposed to be. If I go to negative 2 and then rotate, remember positive is counterclockwise. So if I rotate 120 degrees from here, I'm actually down here in the 4th quadrant. Okay, so my ordered pair that I got for the rectangular was this, and that actually works. Okay, so that actually is 1 to the right and down 0.866 or something. Okay, so just a quick note. So negative 2 cosine. Okay, let's do this in the calculator just so I'm going to do it in radian mode just so you can see that it actually works. Okay, so negative 2 cosine 2 pi over 3. There was my y value. I'm going to cheat a little bit here and just go back and grab that. And I'm just going to hit the sign button where it said cosine. And that is, well, the square root of 3 is 1.732. So this was my x that I calculated, and this was my y value that I calculated. Okay, I just got it using the exact values, the simplest radical form. Okay, well, I want to show you something that is going to be kind of bizarre looking. And you are used to seeing graph paper that looks like this with lots of lines, making a grid. And there is such a thing as polar graph paper. And here it is. This is what it looks like, something like this. And the whole idea, I mean, you need to kind of picture this is the x-axis. This is the y-axis. But really, it's not about x-axis and y-axis when it comes to polar. It's about a distance out from the center and an angle. Okay, so everything's going to be measured from here. This is 0 degrees, 0 radians. Okay, and again, if you're going this way, it's positive. If you're going this way, it's negative. And so this is really easy to graph on. So like for instance, if I had, I'll call this A, we'll just letter them in order. Let's say 57 degrees. So I'm going to call this 1, 2, 3, 4, etc. So I can come out 1, 2, and go to 57 degrees. Well, this would be 45. This would be, these are marked out. Now, if you notice, this is 90, and so halfway would be 45, and these would be 30. So each one of these little guys is 15 on this particular setup. Okay, now there are different versions of this, so you have to kind of pay attention. Sometimes all they'll have is like the circle and then some 45-degree lines. So you have to pay attention to what's there. Don't assume it's always 15s. Okay, you can think about how the circle's divided up and make decisions based on that. Okay, so if I'm going to, again, I have 2, and I'm going to go to 57. Well, this would be 60, so it's got to be a little short of that. So here it is. Here's A. Okay. If I did, let's say B is at -5. Let's go 5 pi over 6. Okay, so I'm going to do this 2 different ways. Okay, so -5 would be 1, 2, 3, 4, 5. And then 5 pi over 6, if you recall, is 150, 5 times 30. So here's 30, 60, 90, 120, 150, and I'm supposed to be right here. Okay. Now, what some people do instead is they'll measure the angle first. Okay, so like for instance, I could do the 5 pi over 6, the 150, and go 30, 60, 90, 120, 150. Okay, so I'm on this line, and what I'm going to do is my distance is going to be negative, so I have to go backwards 1, 2, 3, 4, 5. Still get to the same spot. Okay. Let's do one more point on this graph, and let's do 5, -30 degrees. Okay. So 5, -30. So 1, 2, 3, 4, 5, -30. Well, so here's part of the problem, is there are multiple ways to name the same point. You know, in rectangular coordinates, there's only one way. It has that x value and that y value. Well, with angles, you can name them positive or negative, front, you know, so you're rotating frontwards or backwards, and you can also talk about positive or negative distances from the pole, from what we think of as the origin. So that can be confusing, but in some ways it lets you do some repetition of things too. All right, I just want to do one more thing, I guess, and I'm gonna do 2, but I'll try and go quick. Okay. All right. So theta, we can have equations in polar form also. So for instance, I could have theta equals 30 degrees. Well, let's make a little table of values. This will be r, this will be theta, and for every one of these points, theta is going to be 30 degrees. So that means r could be anything. You know, when we do this in rectangular, it's either a horizontal or vertical line. X equals something is vertical, y equals some number is horizontal. Well, so like this could be 1, 2, 3, -5, -10. Okay, so we'll find the 30-degree line. Here's 130. Here's 230. Here's 330. Well, -530. Let's see, 1, 2, 3, 4, 5 would be somewhere around here. Okay, and again, I'm numbering this 1, 2, 3, 4. Okay, so this is actually a line going through the pole. Isn't that bizarre? So things are different because it's a different kind of numbering system. Okay, if I had the equation r equals 3. Okay, let's do a table of values. So all of these r values would be 3, and I could have angles like 0 degrees, I could have 23 degrees, I could have 516 degrees, I could have 180 degrees, but the radius is 3 for all of those. So if I come out to 3, here's 3, 0. 323 would be somewhere around here. 516. I'm going to go all the way around 360, and then around again puts me at 540, so not quite that far. So I'm somewhere, I don't know, I'm guessing, around here. 180 would be here. Well, all of the points that have an R value of 3 are actually going to make a circle centered at the pole. Okay? So typically, if you have R equals a number that's not 0, then you're going to be talking about a circle. Well, and of course things can get goofy. Let's do R equals 1/10 theta. Okay, so if R is 1/10 theta, so when theta is 0, oh, sorry, so is R. All right, that'll work. When theta is 30, R is 3. Yeah, I needed to make that a smaller, not even 1/10, smaller than that. Okay, when this is 60, this is 6. When this is 120, this is 12. So I'm going to be off this screen in no time. But here's the idea. Here's 0, 0, 3 and 30, 6 and 60. Well, 6 degrees is here, and 6 I think is off my screen. So really what's happening is a spiral. Okay. All right, let's do one more thing. I know I already said that. I'm just going back to the same thing I was doing. R equals 1/10 theta. I'm going to change this. Sorry, it's kind of like when your pastor says in closing. What's it mean? Nothing. Sorry, just teasing. All right, where am I? There I am. Let's do polar. So we did this a little bit with parametric. Now look at this. This is R. And I'm going to do 1 divided by 10 times, I'm going to push that xt theta button, and when I push that xt theta button, sorry, it actually does theta now. Okay, let me go to window, and I think I'm in degrees. No, I'm in radians. All right, I'm going to go to degrees just so you and I can be on the same page as we were before. Window, I'm going to go from 0. I'm going to go to 1440. 1440 is 4 times around the circle. Okay, and I already told you about the step, and this is similar to in parametric. This tells you how often, or how it's going to count when it's doing points. And I don't want to be here all day, so I'm going to go with 5 because I got to go to 1400, and that's a lot. Okay, and I want my screen to be kind of big, I think, so because it's going to come out kind of big, and we might have to change this. So I'm going to go from negative 15 to 15 and negative 10 to 10. The ratio of the size of the screen is roughly 2 vertically to 3 horizontally. So you can play around. And here it comes. Oh, I'm gonna make these even bigger. That's kind of sweet. This to me is the fun of polar. And so I'm gonna go. Let's do negative 90 to 90, and I'm going to number by tens, and I'm going to go 60 to 60, negative 60 to positive 60, again numbering by tens. All right, let's hit the graph. Now, if you think about this, you know, we can trace on here and watch what's going on. Now, I really don't want that kind of tracing, but that's fine. You can just kind of picture what's going on, and we'll fuss with playing with mode stuff later. Look at, as the angle gets bigger, the radius gets bigger. But that should make sense because, you know, if you're looking at the equation here, you know, you're multiplying theta by 1/10. As theta gets bigger, the answer gets bigger. So the radius is the answer. It gets bigger. Okay? All right, well, this is already going longer than I wanted it to go. We will have to talk about converting equations, but it's the same kind of thing as converting points, and we will play with this in class. Okay? Well, this is it for Sanford Flip Math this time. Thank you for watching. Polar, it's kind of fun. I think it's kind of fun, but, you know, I'm a math geek, so that's what happens. And we'll talk to you later. Sanford Flip Math, we're out. Bye.